Thank you everyone for joining us today. I'm Elizabeth Rojas. I'm the Cincinnati 2030 District Director. And today we're going to be joined with three of our valued professional partners from HEPE and Siemens and Malink. We're going to talk about, they're going to share with us some insights on managing a BAS system and demand controlled ventilation, and really how that interplays with in our energy efficiency and meeting our 50% solutions reductions. So today we're joined by Tim Foster with Siemens, Matt Meyer with Malink, and Jeremy Falber with HEPE. So this is part of our 50% solutions series. I think this is a great way to kind of continue the conversation about where we're going as a district and how we move our buildings in the right direction. It's really urgent that we start to address these things. And I think it's also timely, not only from the fact that we have a pandemic which allows us to make improvements to our buildings, but also it's really important to help navigate how we bring people into the building when we bring more people back into the workplace, and how we provide a healthy space yet meet our goals. So without further ado, I'd like to, I'd like to hand it over to our team here.
Thanks, Elizabeth. My name is Tim Foster. I'm with Siemens, and I work in the local Siemens Cincinnati branch office, and we serve Cincinnati, Dayton, Louisville, Lexington, that kind of general market area. So very pleased to be here, and I think this is a great conversation to try to figure out in this day and age how we advance the energy efficiency and how we kind of resolve that with some of the public health issues and healthy environment issues that we're all kind of faced with in the near term and quite possibly for many years to come. So I'm going to talk about building automation. I've got 4 slides. I think I can move through this fairly quick and leave some time for questions at the end or a conversation or a discussion at the end. I want to talk about building automation systems, really how they're evolving to create a healthy environment. And if you look at the slide there, the traditional focus of building automation has really been on operational efficiency. And that could, mean energy savings. It could mean manpower efficiency due to central monitoring. It could be to reduce a building owner's risk. Could be increasing reliability, compliance, automating processes that used to be manual, all of those things. But kind of the commonality is that they're all kind of back office operational efficiency concerns that building owners and managers have had. More recently, and this predates the COVID environment, is that the user experience is becoming more and more important. And this really emerged a couple of years ago to kind of go beyond, basic comfort and meeting code requirement to how can a building provide a more proactive approach to health and comfort, and not only provide it, but in some cases prove it. So where's the data to prove it? And that's meant things like more control over the environment. If you compare working at home, how we can basically have the temperature the way we like it, the lighting the way we like it. We've got a refrigerator close at hand. So basically you control your environment completely working at home. Where you shop, live, or work, or any public buildings, you have less control. So the idea is how do we provide more control in buildings where we not only hope to spend more of their time, but employers are now saying, hey, how do we provide some amenities to attract people back into these spaces and make sure they understand they're comfortable. So that's kind of the challenge, is maintaining that traditional operational efficiency, adding in user experience. And the combination of those both we call smart buildings, but you can kind of pick your definition, whether you want to call that a smart building or high performance building or any other term you might want to use, but it really combines those two underlying features, is operational efficiency and user experience. So you can bounce to the next one, Tom, the next slide. So before I talk about the indoor air quality toolbox and what a building automation system might be able to do to help improve indoor air quality, wanted to talk a little bit about what the basics of BAS. And if you ask me what are the kind of the defining features of a building automation system, and we use the term building automation system, you could also call it an EMS, an energy management system, an FMS, a facility management system, a BMS. None of those terms have any particular meaning, unfortunately, in our industry, but so they're all somewhat interchangeable. But a building automation system, most people would tend to believe is kind of HVAC centric, since that's kind of where the term is most often used, but it's not exclusively there. It could be used to refer to any building operational technology, whether that's lighting, life safety, security systems, power monitoring. There's a myriad of systems in today's buildings that all have some building automation functions that could be called a building automation system. So getting back to like the basics of a building automation system, really there are kind of three things in my mind that stand out of what are critical. One is analog to digital conversion. So mechanical, electrical systems are, we live in an analog world, but we convert those to digital values. So that's really what a building automation system does as a first step, is take all this analog information through temperatures and sensors and so on, converts that to a digital value. And then once it becomes a digital value, it's software. And all of those features can be manipulated through what we call a sequence of operation. So that's one feature. The second would be connectivity. Typically, you'll have multiple controllers, will form a network, and those controllers are able to communicate in some manner to form more of a cohesive network platform in a building. So that's the connection feature, so that different building functions can be shared, not only the data, but the outputs and sequence of operation and automation functions can be shared. And the third item you see in the upper left-hand corner labeled management workstation, almost all BASs have some system interface which enables an operator, an engineer, or even space users or other interested parties to visualize all the building functions. And that's typically through graphics that are symbolic of the operations. That could be reports, historical trends, and a number of other interface type functions. So if you think about that, analog to digital conversion, ability to connect, and visualizing system interface, that might have been a kind of a unique definition 10, 20, 30 years ago, but you look at that through a modern lens, and there's really nothing unique about building automation functions compared to IT in general. And that's really kind of leading us to where we're at now, is that we're spending all of our life now, or a good part of our life, in this digital world. And now from a building operational technology, we're seeing a convergence of OT and IT. And again, that convergence goes by different names. Some people call it the Internet of Things. That could be cloud computing. That could be a number of different technologies. But there's definitely a convergence, which means that the traditional definition of building automation systems is becoming kind of rapidly obsolete. So moving to kind of indoor air quality, you can see I've listed some devices there. And this isn't meant to be a technical deep dive, other than to say that temperature, relative humidity, carbon dioxide sensing, particle measurement, airflow stations, occupancy, lighting level switches, all of that data can be brought into the building automation system. We can develop a unique sequence of operation, and we can control the building accordingly. And the lines you see aren't necessarily literal lines where it means that say a particle measurement sensor needs to be wired through a wire back and landed on a controller terminal. That data can be acquired in a variety of different ways, including from the cloud, from different systems, subsystems within the building. So So really the kind of the possibilities right now are fairly limitless in terms of how this can be done, and really up to the kind of the creativity, imagination, and in some cases the wallet size of a facility manager that's interested in kind of combining these technologies. So next slide, please. So my last two slides, I want to get into kind of some general recommendations on what we could do to kind of continue energy efficiency, but still provide that holistic high performance building that can really respond better to user requirements, and particularly, healthy indoor air quality requirements. The first one is this idea of systems optimization, that all systems in a building should be interconnected. And we've seen over the years where, energy savings at one level, say you do something to air handling units or something, your central plant, you save energy in one place, there's an energy penalty somewhere else. So this is kind of recognition that all systems within a building could be interrelated and optimized. And as the chart indicates, all of those decisions should start with the load, and load we would define as the actual space and the people in the space. So if we kind of use that to reset our building strategies for air handlers and central plants, we can gain a lot of energy efficiency and still make sure we maintain adequate space conditions. So that would be one. The second one, Tom, if you could advance. So this would be the last area where we can combine energy efficiency with better building operation, better building performance, and that's the whole area of fault detection and diagnostics, which in the building automation industry has really kind of taken off the last year or two in terms of being able to deliver not just the idea, but practical, cost-effective solutions. So this is just by the way of a metaphor. The difference between a fault detection and an alarm. In your car, the oil temperature light, that's probably an alarm. That's a single sensor, discrete point, wired to a light on your dashboard. It tells you have an alarm. It really doesn't tell you the problem that was causing that, nor could it have told you in advance that was going to happen. Whereas fault detection is more proactive in trying to identify, looking at all the variables on HVAC, lighting, other building functions, looking at all those variables almost in a kind of a deep data mining sort of way, trying to figure out those interconnecting relationships, and then try to identify things that ordinarily would be difficult to see unless a trained operator was, specifically looking for it. Like a damper that wasn't working, or maybe a valve that was leaking, but you wouldn't know that because something else in the system was wasting energy, but it was compensating for a leaking valve. So that's kind of the idea behind fault detection diagnostics, is not only can you, look at this information coming from the building automation system, but you can also use decision rules to help prioritize which items are costing the most energy from a dollar standpoint, as well as maybe have the biggest impact to operations or users, and you can also integrate that data with workflow processes. So it could be integrated into a building's, maintenance routine or work orders or preventive maintenance, work order system. So typically we see, and through fault detection, and another term for it is continuous commissioning, but through this automated fault detection or continuous commissioning approach, typically you see 10 to 20% energy savings, kind of rule of thumb, sometimes more, depending on where you're at. But really the opportunity for manpower or energy or operational efficiency savings is probably greater than that. I mean, we might see like a 2-to-1 between energy and operational efficiency. So from that standpoint, you could see some pretty significant operational savings, because now rather than doing maintenance based on a time routine or a rule of thumb, changing the filter every 6 months, now you can do it based on actual demand and kind of prioritize those issues in terms of impact on the organization. So that's fault detection, and that's all I had from a prep standpoint. And I've got a minute and 48 seconds to the good left, Tom, so I will hand off the baton.
Thanks, Tim. For any of the participants, feel free to type your questions into the chat, and if you could do us a favor and direct your question to whoever you'd like to answer, that would be helpful. But thanks, Tim. That was a great overview. We'll now move on to our second presenter with Malink and Matt Meyer, who I will introduce briefly. Who will be discussing considerations for increasing outdoor air ventilation. Go ahead, Matt.
All right. Thanks, Tom. I appreciate that. So I'm Matt Meyer. I've been with Malink Corporation since 2015. I've been on the test and balance side of the house for about 3 years now. So having a pretty good time doing that. A lot of this stuff was new to me a few years ago, so it's been an interesting learning experience for me so far. So yeah, I'm with Malink. So once the presentations are all done, you'll have my contact information, be able to reach out if you guys have further questions beyond today. Go ahead and advance, Tom. So just real quick, Malink, and I won't take up too much time. For those of you that haven't been there, I know there's quite a few people in the area that have been out to see us. And I know during the pandemic, our what do you call it? Our tours have gone down considerably. We haven't been doing very many at all. But once this is all behind us, we would love to have people back out where we can actually show you how we demonstrate a lot of the principles that that both Tim have talked about, that I'll talk about, and then Jeremy as well, just in operating our facilities. Go ahead and advance again, please. So I'll go through real quick. I know most of you all know this kind of stuff already, but just to have a brief overview of how buildings function from an HVAC standpoint, and then we'll start talking about the different benefits of why you need to increase the outdoor air or the outside air, and then I'll also provide some recommendations on how you can go about doing that. So please move forward. So some of the relevant standards, and I didn't realize this was a build slide, Tom, and I appreciate you jumping through there. Some of the stuff that I'll talk about, it comes from these different standards. By and large, when you're dealing with HVAC, specifically when we're talking about ventilation and indoor air quality, we're dealing with ASHRAE 62.1, and its most recent version came out in 2019. They've got two different standards, 62.1, which is the general, and then they've got low-rise residential buildings at 62.2. Those are the big ones that I know I deal with most often. These other standards out there are just as important. Feel free to use this slide going forward to be able to go in and research this stuff yourself. But I'll touch on different parts from different organizations as we go through the presentation today. Forward, please. So I pulled this out of the ASHRAE guidance for reopening of schools, particularly. I thought it was a very good quote to really help. They put out, ASHRAE put out a lot of guidance over these past 9 months about what we should do to get schools back open. Specifically speaking, ventilation, a good supply of outside air in accordance with ASHRAE standard 62.1-19 to dilute indoor contaminants is a first line of defense against the aerosol transmission of SARS-CoV-2. So SARS-CoV-2 being the virus that creates the COVID-19 disease. Go ahead and move forward, Tom. You can build this one out all the way. So an HVAC system is your building. If we just take, we deal with a lot of small restaurants and stuff like that, but it's, back up one more, thank you. We deal with a lot of restaurants and stuff like that. So this is a kind of a dumbed down version, but to make it as basic as possible, your building needs a function. You need air in order to keep either your customers or your tenants comfortable. You bring air into the building. That air is heated, cooled, whatever the situation is, dehumidified, filtered, all of the above. A certain amount of that air is then exchanged. It is exhausted in one way or another. Ideally, the building is to remain in a positive state at all times to help keep unwanted contaminants. That could be air, it could be insects, it could be anything. You want to keep your building in a positive state. this is the general design. This is what most engineers, if not all, they seek to have a positive building pressure at all times. So the idea is the more outside air you bring in, the less recirculation you need to do within the building. And I'll talk a little bit more about the recirculation of air as we go forward. Go ahead, Tom. So there's pretty much 5 pretty solid pillars that we like to touch on when it comes to system function and building health. Temperature control is very, very important. So OSHA specifically recommends facilities stay between 68 and 78 degrees. I know not many of us like to be in a building where your set point is lower than 70 degrees. It gets to be quite uncomfortable. But that's also, that's beyond just comfort. There's health within comfort as well. So it's important to make sure your temperature is at a reasonable state. Moisture and humidity control is also very important, and this fluctuates between different standards. I wanted to put in here the International Well Building Institute recommendation specifically. So they're recommending between 40% and 60% relative humidity within your space. They believe that will help limit the spread and the survival of the COVID-19 disease or the virus within the building. And then ventilation, and we'll touch even further on ventilation. The introduction of fresh air, fresh outdoor air, helps removing polluted air. So the 62.1 is pretty broad. It's not a one size fits all for every building. So if you're in a hospital, you're going to have different standards or different recommendations, I should say, within 62.1 that you would have in a school. So it is very important that you consult this guide, the ASHRAE guide, to understand, how your facility should be set up or what the recommendations are for your facility to be set up. And then next is pressurization of the building. I touched on that on the previous slide. You want your building to be at a slightly positive. You don't want it to be at an overly positive state where you're bringing in lots of outside air and then just blowing your doors open. That's not what you want either, because that doesn't leave everybody in a good comfort space. But it is there's a happy medium that you find there. You can jump to the next slide. So this is touching on filters. And I know Tim briefly touched on filtration and with the BMS systems and how it kind of interrelates. So keeping your filters clean, Tim was talking about, the BMS systems can let you know when your air filter starts to become too clogged or too dirty. That's great. And that's a really big benefit of the BMS systems that are out there, because they can start to help maintenance providers understand what's going on with the building before it actually becomes a major issue. Right now, specifically with COVID-19 going on, there's a lot of recommendations, and most bodies are recommending the use of the MERV 13 filter. If you can see the chart very clearly, I know it's kind of small, you can see that there's lots of different MERVs out there. And there's even more than just these 4. There are actually MERVs beyond the MERV 13. MERV 13 is the first MERV level where it starts to capture bacteria and virus carrying sizes. And so that tends to be the first one that gets thrown out there. The higher that number gets, obviously the more expensive, the higher probably the smaller or the lower on the supply chain you'll be able to find them too. There's probably less of them out there. But the increase of your MERV filter really needs to be, and I think Jeremy's going to talk about this too, you've got to kind of weigh the pros and cons between how much MERV or how strict or how much restriction can my filter allow before I start using too much energy on my unit. That's a very important factor here. So what we're trying to suggest here is increase that MERV filter as much as your system will allow you to do that. There could be a system, you could have a building where you've got 4 different types of RTUs. Half of your RTUs can all take a MERV 13 with no problem. Just had to do a little bit of a speed increase on your fan. But then your other ones, they're already maxed out. They're already near their FLA. If you try to increase any more restriction, the static's going to be too high, and you're not going to be able to do that. it's not going to be good for your equipment. It's going to end up breaking. So you've got to weigh that balance. The next line is ensuring the proper fit of your filters. This seems like a no-brainer, but being a test and balance firm that Malink is, you'd be surprised at the number of jobs we go to, and the filters are just loosely in there. A maintenance personnel has literally just stuffed in whatever size filter they could find. And without having that whole filter tray filled up from end to end, top to bottom, you're just allowing air particles to move around the filter. Of course, you're going to get some to go through the filter, probably most of it, but you're still allowing contaminants to go around that filter, which is definitely not what you're looking to do, especially, during COVID-19. So anyway, next slide, please. So this is just a pretty graph that we had that we like to show. So carbon dioxide, or IAQ, very important. Understanding how that's interacting in your building, your humidity, your building pressure, and your temperature. These are all components that really relate and really help you keep and maintain a healthy building. Next slide, please. So the transmission of SARS-CoV-2 through the air is sufficiently likely that airborne exposure to the virus should be controlled. Changes to building operations, including the operation of heating, ventilation, and air conditioning systems, can reduce airborne exposures. That's straight out of ASHRAE. So their first recommendation is to start increasing your outdoor air at some degree. Next slide, please. So some of the benefits. Ventilation dilutes the contaminants. I think that's pretty self-explanatory. The wording here is really strange. So it says, thereby increasing the exposure time required to receive an infectious dose. I went back and forth trying to word this better, but I really couldn't. So it's just going to be better to kind of talk through it. So right now they're telling us that if you're in the presence of someone with COVID-19 without your mask on for about 15 minutes, you're considered to have been exposed. What ASHRAE is mentioning here in their fundamentals of COVID-19 risk management is with increased dilution, you can increase that number from 15 to something closer to maybe 18 or 19. They don't provide any hard numbers or anything like that. It's simply a statement, but it makes sense. So, the infectious dose, your time in the presence of that infectious dose could go up potentially. Very important to consider with outdoor air. It needs to work in conjunction with your exhaust and the pressurization of your building. If you're going to increase the outdoor air, obviously you need to increase your exhaust at some point to keep that building at a decent pressurization. This reduces your air stagnation because you're not just recirculating the same air through your building all day long. And then the reduction of recirculation of potentially infected air is pretty self-explanatory as well. A lot of this stuff is pretty easy concepts to grasp. And then it's an increase in the air exchange in the building. Of course, you'd rather have a building that is getting filtered air pulled through it at a more frequent pace than you would a less frequent pace. Next slide, please. Pretty simple. The CDC likes to break it down. Increase air exchange in the building. Next slide, please. So how do you do it? Number one, the very first step that you need to do is you need to find an engineering firm or a certified professional that will help you understand the best options for your building. So find an engineering firm. Heapy's a great engineering firm. Talk to them or someone like them to propose certain measures for your building. They'll use ASHRAE, they'll use CDC, they'll use LEED, they'll use different standards, and you can request certain standards that to be used as well, and they'll help you. The next step is to have a certified TAB firm, test and balance, come in and properly measure all your air, not just your outside air. Then they'll be able to provide you, those two sources will be able to provide you with the proper recommendations to tell your maintenance team or your preferred contractor to come out here and actually make changes to your building. Next slide, please. So this isn't a new concept, the increase of outside air on your building. It's not new. This quote comes from a document that Darren from Malink We're doing some research. This is from the CDC guidelines that they put out before COVID-19 even hit. So engineering the controls in your building to contain or prevent the spread of airborne contaminants center on local exhaust ventilation, general ventilation, and air cleaning. General ventilation encompasses dilution and removal of contaminants via well-mixed air distribution of filtered air. Again, it's one of the basic tenets of what the engineering firms do when we're designing buildings. And then when we're out doing the test and balance on buildings, it's the same thing. We're trying to make sure that that engineer's design is being met. A lot of people with older buildings, you have to get that checkup done and make sure that this kind of stuff is happening to ensure that your building is performing the way that it was meant to perform to begin with. And then with COVID-19, it's even more important to have that checkup done. Next slide. So that's it for me. And I'm going to pass it off to Jeremy at HEPE.
All right, thank you very much, Matt and Tom. So I'm going to talk about system impacts for increasing that outdoor air. And the way I went about studying this is to start with an energy model. And we took an energy model for an existing, or for an office building, a new office building. It was approximately 36,000 square feet. It's a VAV mixed air system, so it is recirculating air. It's not 100% outdoor air. I looked at this in terms of having a fixed outdoor air CFM. And so what that means is even as your recirculation air increases or decreases, the outside air quantity always stays the same. That's the way ASHRAE 62 wants you to do it. And the reality is, in order to do that with a VAV system, you likely need airflow measurement to be holding that set point. So you may not have that level of control for your building, but that is what is suggested and recommended. I'm going to look at utility costs and how that deals with it, and then other impacts that it can have to your equipment. Other information about this building is the baseline average for it was about 24% outdoor air of the system total. On the next slide, I'm going to be talking about increases over that baseline. So a 50% increase is taking that from 24% outside air to 36% outside air. It is not to a 50% outside air total, which would be about 100% increase. Another element that's going to be with this is your equipment efficiency will impact your energy usage a little bit. Less efficient, you're going to use more energy. More efficient, you're going to use less energy. And then these are also based around a fully utilized building. Something that is going out there on some level for some buildings is you have lower people, lights, equipment. So some of these numbers may go down or up for that, and we're going to talk about that a little bit more at the end. And then the other thing is these are all energy model results, and it's best as a comparative tool. And so I've put everything in terms of a percent change, not in terms of like a hard limit change of BTUs or dollars. And so hopefully that will be scalable for you. So this slide here deals with cooling increases only. This is looking at your cooling equipment. There will be other electricity items that change with this in terms of fan power, but that's not included. This is just looking at your cooling energy usage. The blue bars represent the cumulative increase in cooling energy compared to normal operation. And so for every hour that you've got this 10% outside air above what that normal would be, basically above, say, 75 degrees, because the building that we modeled had energy economizer, air side economizer. So it was already going to be 100% outside air up until about 75 degrees. But at that 10%, you look at all the hours where it's slightly above that, it only equals a 1.4% energy and cooling energy used throughout the entire year. However, we see with the orange, the impact that it has to the peak that is required of that equipment. So we can see with this that overall, it doesn't have a huge percent increase in energy compared to what it uses throughout the year, but it does impact the peak. I would expect a normal piece of equipment size by most engineers could probably handle a 10% increase, which in this case is just taking you from 24% outside air to 26, 27% outside air. You get around that 20 to 30%, unless your engineer really over designed it a lot, you will probably begin to experience some comfort issues at various points throughout that year. Those comfort issues would come from a higher temperature than maybe you desire, as well as a higher humidity. At the very right, we see with the 50% increase that that's as much as a 16% impact to your equipment. And it's important that you look at your system and what that means. In the case of like a package rooftop unit where it already has a compressor, that's what you're really talking about is, can that unit itself handle that percent increase versus a central system like a chiller. With that sort of system, you have to look at not only can the chiller capacity handle this percent increase, but can the individual chilled water coils handle that? So you might have the capacity at the chiller because of diversity and how that chiller was sized, but you wouldn't have the capacity at the coil to deal with those increases. On the next slide, we'll look at heating. And here the colors mean the same thing, just for a different energy source. The blue would be the cumulative heating impact. We see that these are significantly higher. And what this does is it kind of shows that you're going to have a lot more hours of operation in the heating where you have to deal with this increased energy. And the reason for that is our VAV systems tend to provide less air as you operate at cold temperatures. You just don't need as much air to heat the building. And so, your outside air percentage really gets a lot higher when you're in these colder temperatures. It starts out at that 24% on a peak day. As it cools down and my VAV drops to like 75%, now I might have been 30% outside air. When it gets down to 50%, I'm now a 50% outside air unit. So that's why this percentage increase is so much higher. I want to draw a little bit of attention to the orange. While this looks like it has a lower impact on the heating equipment, if you look at the percentages, all of them are actually higher than the cooling. So even at the 10%, there's this 3.7% increase in peak capacity versus 19.4% at the 50% air increase. So this again has your impact to that equipment that you got to look at. This should just really be your central equipment, not your VAVs, as those should still be seeing the same temperature. The only way it would impact that is if you are unable to maintain your typical discharge temperature at like a central system. This is going to have the same caveat that I had for cooling of your system type may mean you have to look at one or two things. If you're a gas-fired rooftop unit, you really just need to look at that gas-fired coil. A lot of times, based on my experience, those are oversized based on selection. So you may be able to do, a 50% increase in outdoor air for heating, but not cooling. Whereas if you have a central system, you have to look at both, do I have the boiler capacity as well as what can my coil? And in both of these instances, you really want to get a professional to look at that and tell you what your equipment's capable of. Next slide, please. Couple more. All right, so this one looks at the outdoor air energy and how that affects your energy cost. So in the blue, we have total impact to electricity. In the orange, we have the impact to the gas. And in the green, we have an impact to the total cost. So the orange actually matches the previous slide where it is the same percentages as the what was the blue line, because the only gas usage in this building was for the heating. In other buildings where if you have domestic water that's gas, domestic water heating that's gas, or like a kitchen that's got a gas service, these percentages would lower from that peak. But that we do see a pretty significant increase in gas energy usage from this. For cooling, we see a smaller impact. The reason for that is you have a lot of services in a building that require electricity, but don't impact the outdoor air, doesn't really impact their energy usage. So examples of that would be your lighting, your equipment in terms of computers, anything like that. You know, that needle electricity isn't moving. So there's really very small percentage increase in electricity. However, electricity does typically cost about 3 times as much, 2.5 to 3 times as much as gas in terms of a BTU usage. So that's something to keep in mind as well, that even small electricity amounts can be quite significant in terms of dollars. If we look at the building breakdown, the reason the green ends up so much smaller is partly because of that difference in cost between gas and electric, and partly because in our models, heating just doesn't get used as much as electricity. I think in real life that ends up being a little less skewed, and there's a little bit more gas costs typically experienced. But just as a reminder, these numbers in terms of cost are going to shift based on the efficiency of your equipment. If you've paid to put more efficient equipment in, it can deal with those increased energy requirements more cost effectively than if you didn't put those in. So for our next slide, we want to talk about how the equipment life is going to be impacted by this. One item I want to talk about is unoccupied hours, which something Matt didn't go into, is one of the suggestions out there by CDC and ASHRAE is to deliver outdoor air and recirculated air during either post-occupancy or pre-occupancy. The idea to flush out the air, if you think about it, someone's in there breathing, talking, bioaerosols going in the air. It takes a certain amount of time of air recirculation to get that out. And so one of the ways of dealing with that is when you've got a building that's only going to be occupied, say 13 hours throughout the day, either after people have left, keep running the HVAC system and kind of clean out that air. So when people come in the next morning, it's clean, or you can do that just before people come in. We looked at increasing this from like a 13-hour day to a 16-hour day, which is about a 23% increase. Electricity increased by 4.6 to 6.3%. So that was kind of in the mid tier of the 20 to 30% on the previous slide. And then, well, I'm sorry, on the cooling slide, 3 back. And then gas increased from like 9.3% to 12.6% in terms of energy usage by doing those unoccupied hours, increasing up by 3 hours. Interestingly, at least to me, cooling energy increases were dominant when flushing at post-occupancy, and heating energy was dominant when flushing pre-occupancy. This kind of makes sense, and so I think a counter-seasonal approach could minimize your cost even further. And so what that would look like is you flush post-occupancy in the winter. So when the building closes, that's when you want to do your flush in the winter, because while it's cold outside, it's not as cold from like 6 to 9 o'clock as it is from 5 to 8 o'clock in the morning. And then in the summer, you flush in the morning because that's going to be your coldest part of the day, versus in the evening where it's maybe not your warmest, but certainly on the warmer end. Next item is filter replacement. As you bring in more outdoor air, you are going to bring in more particulate. Your outdoor air from a particulate standpoint has more particulate. it's dirtier in that sense. It's typically cleaner in the sense of at least viruses and maybe bacteria and mold. Hopefully not mold though. But increasing your unoccupied hours will cause more particulate to be on your filters. Just increasing your percentage of outdoor air will cause more particulate to be on those filters. Both of those would point towards maybe having to replace your filters more often, but a lot of times that's going to depend on your method. If you look at healthcare facilities, particularly hospitals, those operate 24/7. They typically do not replace their pre-filters any more frequently than office buildings, from what I'm aware. So I don't know that it really will. If you're just on a set schedule, I would be a little surprised if you're going to have to increase your filter replacement. If you're not on a set schedule and are doing it off of measured pressure drop monitored through the BAS, then you probably are going to have a little bit faster filter replacement, but that's, I don't know how much that's going to shift it, because it's both recirculated and outdoor air. Maybe it causes you to do it 1 month earlier or something like that, because you're a small percentage increase. The other item is equipment run hours. If you are doing unoccupied hours operation, then your equipment run hours are going to increase somewhat proportionally to those unoccupied run hours. So in the example I gave before of going to 13 hours a day to 16 hours a day, Monday through Friday, that's about a 25% increase. You're probably going to get about a 25% increase in equipment run hours in a year. Probably slightly less, because a few of those hours will end up have been some unoccupied operation at some points, but more or less the same increase. If you're looking at just increasing outdoor air, that really has a marginal impact to equipment run hours. Your equipment's still going to have to turn on for cooling at about the same outdoor air temperature. If you're in cooling, maybe a little bit sooner with a slightly cooler temperature, with a slightly warmer temperature, because you've got just more outside air brought in. And if you're in heating, as you'll probably have to bring it on at a slightly warmer temperature, just because of the greater quantity than you otherwise would have. But I would anticipate a marginal amount of hours being run. But what you're going to do is you're going to run your equipment at a higher percent load throughout the year from that increased outdoor air. So instead of being 25% loaded, you're going to be 30% loaded more hours. That's not generally understood to have a big impact on equipment. It's more about the number of cycles and run hours, not the percent load. And you may even see less equipment cycling by having this higher quantity of outdoor air. One item I did want to caution on as you look at these increases in outdoor air is you do have to be able to deal with relief. And so that comes into your into what your fan is capable of. Your outdoor air fan is bringing in outdoor air doesn't really require a whole lot more supply fan, because it's just you're taking two different paths. You're increasing your outdoor air as you decrease your recirculated air, but your fan's still moving the same amount of air. Your relief fan may end up moving greater amounts of air because of that increased outdoor air. So that's where some of the additional fan energy may come in, as well as just making sure that your fan is able to handle that higher peak. And next slide, please. Want to touch a little bit on lessons learned. I'm going to say these are anecdotal, just because it's really spot cases of talking with individuals. The buildings that were looked at were generally occupied with fewer people, and it was a stated goal to be at 50% of their typical occupancy. What they found is they operated with lower than normal utility bills in the summer, but higher than normal utility bills in the winter. And during the shutdown back in March to April, they saw about a 20% decrease in energy, which was less than they expected for unoccupied buildings. For the learning curve, we were cautioned that your building operations are going to change, and you need to be prepared to make adjustments to your BAS sequences for that. An example that was given was their hot water resets were no longer working the way that they needed them to work. And so they had to keep a closer eye on the building after adjustments were made, and just look for differences in how the building responds to items. And then the last item I wanted to touch on was this hydronic equipment safety. Once you introduce hydronics into the airstream with greater amounts of outside air, then freeze potential becomes a concern, particularly in this area of the country. With that increased outdoor air, you want to make sure that your safeties are working correctly. So talk with the BAS contractor in terms of, is there a good way for us to test that? And then the other thing that your professional should be looking at as you're looking at what capacities you can go up to is, are there additional freeze protection safeties that should be in place? Maybe you have a freeze stat, but you didn't have a coil pump. As you move to greater quantities of outdoor air, that coil pump may be justified. So those are just some minor items that really need to be looked at, and make sure that you're not going to abruptly end the equipment life cycle because of a catastrophic failure because you didn't have the safeties in place. And next slide, please. And that's all I have. I think it's now time for questions.
Yeah, great. Thank you, Jeremy and Matt. It was really great, really informative, really detailed, and really well threaded together. So we did have some questions pop up in the chat. I'll go ahead and read the ones that we received. The first question was, directed towards Matt. And if you don't necessarily know the specific answer, it's okay. But I don't know if how much, you talked about humidity levels and the requirements, and the well building standards specifically. The well building standard is informing the Cincinnati 2030 district's healthy building. That's one of the components. And so I wondered if is there any research or you have any anecdotal knowledge of what a 40 to 60% humidity level does to a building's energy performance?
No, I don't have any anecdotal evidence there. I know the only thing that I can suggest is that ASHRAE is already standard. So the standard that most engineers are already using, they use between 30 and 60% as their standard. So increasing that minimum to 40, I don't think is going to have a considerable impact on a building. It's just something that they need to pay closer attention to if they're going to meet that well standard.
Great.
Maybe Jeremy has a better answer to that.
Jeremy, do you have any insights into that?
Well, so there's two items I want to, or I guess a few items I want to comment on. First is the 40 to 60% should be fairly typical in summer operation, late spring through early fall. That's your natural amount of humidity in the air and your dehumidification that you provide should keep you in that range. So what we're really talking about here is winter operation. And it's important to understand that a lot of buildings are not designed to deal with a 40% relative humidity in the winter in their building envelope. And so that's an element that should be looked at before you go down that path. Otherwise, you can easily get mold that starts growing inside your walls. From an energy standpoint, the only thing I can say is from our past experience with hospitals, which do not humidify as high as 40% typically, they're 30% on the kind of high end. I think you see about I want to say it's a 5 to 10% increase in gas usage from that. But you got to keep in mind, they use a lot more energy throughout a year of 24/7 operation. And so that 5 to 10% might be a bigger number for another facility. And so I don't have a good answer for like an office or any other space. The more outdoor air you bring in, the more expensive it's going to be, though.
Great. Another question we got was pertaining to filter selection based on design intent. You each touched on this a little bit, but can you talk about sort of the idea, like filters broadly, and making sure that they appropriately fit the systems, and what people can get caught up on when they're trying to replace filters, depending on what is installed in the building? I'll kind of throw that out there generally, if any of you want to take a stab at it.
Yeah, so I'll take a stab at it first, and then Matt can follow up. I guess one thing, if you're looking at most facilities probably have a MERV 8, unless their engineer wanted something higher. Like we typically do at least a MERV 11 on most of our buildings if we can. Commercial building, maybe not, just a commercial office. But if you're going from that MERV 8 to a MERV 11 or a MERV 13, I think not only is fit important, but you really want to start looking at how is that filter mounted? Because a lot of the MERV 8 filters are just like a slide in and there's really no ceiling. And so you can get bypass air. There's not a big pressure drop across a MERV 8 filter. And so, that bypass air isn't as significant. It's also the MERV 8 is primarily trying to catch large particles, which are not going to bypass as easily. You go to a MERV 13 where you are trying to get smaller particles. And to me, having a better seal at that filter is important. You can still get slide-in MERV 13 filters with the cardboard frame. What I would suggest is maybe doing some sort of weather stripping or something so that at least at that border, it's better than what it was where you're just metal to cardboard. But if you can really change the rack and change the filter mounting type, that is going to be your best solution for a MERV 13. I don't know if that answered your question, but
yeah, it was more of a statement than a question, but thank you. No, I appreciate you responding to that. So it sounds like the overall intent is that there's going to be some nuance to this depending on what systems you have in place, but there are some workarounds depending on what you can easily accommodate to replace filters to meet that higher standard. So thank you. Matt, do you have anything else you wanted to chime in on that?
No, he hit the nail on the head.
Great. Well, great. Well, we got one question, Jeremy, about what energy modeling software you used to generate the charts that you showed us.
Great. So the energy model I used was from Train Trace. And then we also have kind of an internal spreadsheet that we've developed for bin hours that was also used for some of that analysis as well.
Great, thank you. I have one last question, but if I'll give anybody else a chance to ask a question or unmute themselves if they feel so inclined. But I'll go ahead and ask my question, and then if anybody else has another question, feel free to type it into the chat. But we're talking a lot about this in the context of COVID, current pandemic, with vaccines, knock on wood, coming around the corner. My broader question is, how relevant do we think that these ideas are going to persist moving forward? What's your sense of, once larger pandemic is behind us, is there a sense that we'll revert back to some sort of normal operating behavior, or is there evidence to suggest that that these ideas are going to get crystallized and become more of a building standard, as opposed to some pie in the sky idea or some sort of reactionary response to a once in a generation pandemic?
I guess I can start. I'd caution whether it's a once in a generation thing, in the sense of if you go to Wikipedia and you type in pandemic, you will see that there are a lot of pandemics that have gone on, particularly even in the US over the last 20 years. So they've been influenza pandemics, but they've still been pandemics in that they were worse than the typical flu season. There was also the original SARS pandemic, which really didn't come to the US 20 years ago. So they are more frequent than we often think about. Whether there'll be another one like this in my lifetime, I don't know. But I can say I'm heavily involved with ASHRAE at the societal level, and I know people on the 62.1 committee. The last update I got from them, which is a few months old, but their feeling was they were not going to be looking at adjusting the minimum amount of outdoor air. So from a code standpoint, they've not begun discussions of that. I do know I was invited to a meeting here where the ASHRAE Epidemic Task Force is going to be talking about items like that. So, maybe they come up with some different guideline that people begin to follow as a standard of care. Operationally, I think it's just going to come down to people. I would say, from my personal perspective, I think filtration is a lot better method to go about dealing with this than outdoor air. I think filters you get a pressure drop increase with those, maybe, because they do a lot better job making filters now than they did 10, 15 years ago, and have really figured out how to get some of those pressure drops down. So you might be able to go from a MERV 8 to a MERV 13 filter without really increasing fan power, but you are going to increase your filter cost. Your filters might cost 10 times as much to do that. But at least based on a research paper for influenza and what they consider to be a infectious aerosol, which will be larger than the virus, and so even a MERV 8 will get some percentage of those. They were suggesting that a MERV 8 might filter out about 44% versus a MERV 13 is going to be 90% plus effective. That is a significantly better bang for your buck in terms of removing an airborne virus than an outdoor air increase and that energy and equipment impact. So if I were to recommend anything to people, I would look at increase your filter performance before you look at outdoor air.
Great.
Yeah, and I think if I can chime in real quick,
Yeah,
just the broad discussion. I mean, even with some of the standards being adjusted and moved around, I don't think it's so much that what the standard is. Will it change or will it remain? Hopefully, the result of this pandemic is people pay closer attention to their buildings, because I don't think that happens until something like this happens. People start looking at it and saying, oh wow, I really should pay closer attention to what kind of filter I'm putting in here. Some groups do and some groups don't, but that I think is the big takeaway that I think we're going to see coming out of the pandemic is there ought to be a much closer scrutiny taken onto your buildings, your building health, just in general, and keep Jeremy and I in business for a little longer.
Well, great. Well, I'll pass it over to Elizabeth to add some closing remarks, but thank you to you all for the really insightful comments and presentation.
Yeah, that was great, guys. I just wanted to give one last call if anybody has any last questions. Feel free to unmute yourself. Going once, twice. And thank you so much, Tim, Matt, and Jeremy for this great presentation. I think it's really useful in having a conversation with our building owners as we address both the occupant health and the energy efficiency of them in kind of a larger context. And I do think that we are moving to a different time when people are a little bit more aware of what their buildings are doing and asking questions about what they might be doing for them to help them, to support them, and to keep them healthy. So this is a great great place for us to start. And I just want to thank you all for your time today and look for next steps. With our building owners, I hope that the next questions become, what is our building doing? How do we move forward? And please reach out to any of us. We will work to connect you with the right folks to get you on the right path. We welcome those questions. We welcome being a support mechanism for this community. So thanks again. This is the 50% Solutions series, and we appreciate it. Thanks. Bye.